Okay, this is active filter design lecture 9. In the last class, we were trying to synthesize the LC ladder network that resulted in a inverse Chebyshev magnitude response. As an illustration, we chose a third order inverse Chebyshev filter with a stop band frequency of 1 radian per second. The minimum of transmission occurs at the roots of this equation, right, because this is what appears in the numerator, cos of 3 cos inverse 1 by omega z equal to 0, and this goes to 0 for frequencies omega z equal to 2 by root 3 as well as infinity, right. So, then the only finite 0 of transmission is at s by root, s is equal to plus minus j2 by root 3. And then we said that we go through the usual 1/4 h of j omega whole square is 1/4 times 1 minus mod gamma the whole square. The 1/4 goes away. So, we are left with mod h of j omega the whole square is 1 minus mod gamma square, from which we get mod gamma square is 1 minus h of j omega whole square. H of j omega whole square is epsilon square Cn square of 1 by omega divided by 1 plus epsilon square Cn square of 1 by omega, which means that gamma of s times gamma of minus s evaluated at s equal to j omega is given by omega to the power whatever, right. So, it's the square root of 1 by 1 plus epsilon square Cn square of 1 by omega, and then you do the factorization and you end up with the denominator of gamma s being the denominator of the inverse Chebyshev filter that you are trying to realize. Okay. So, we identify the LHP roots of the filter with those of gamma of s. The numerator becomes s cube. So, as you can see, the reflection coefficient as a function of s is given by s cube divided by a polynomial in s, which happens to be the inverse Chebyshev denominator. Intuitively speaking, as s tends to infinity, what would you expect for the reflection coefficient? You should expect 1. Okay, and that makes sense. All right, because at infinity there is no what do you call, in all the power is reflected back. Okay, great. Now, a useful rule of thumb is to retain, especially in hand calculations, is to retain as many decimal places in these coefficients as the order. So, I've been a little more careful here and actually have chosen retain 4 decimal places and continue with the calculations. On a computer, of course, this is not really a problem because the precision of the computer is for all practical purposes infinite. So, the given gamma of s, the reflection coefficient, which is given by z minus z naught divided by z plus z naught, assuming z naught is 1 ohm, what we get is this expression for Zn of s, and we already know the form of the ladder network that we want. So, we know that, for example, to realize finite zeros, one way to do it is to make sure that the shunt arm becomes a short circuit at the 0 frequency, right. Alternatively, the series arm becomes an open circuit at the 0 frequency. So, we choose this example. Zin is given by this expression, correct, and the job now is to figure out L1, L2, C2 and L3 such that Zn becomes equal to this. Okay. This is where we kind of, I think, wound up last time, and there is nothing new here. If you think about it, it is pretty much the same thing that we do with the all pole ladder synthesis, right. when all the poles were at, when there were only poles in the transfer function, for example, in the Butterworth and the odd order Chebyshev case, we found that the network simply becomes an LC ladder, and at each step of the way, what we were doing was letting S tend to infinity and equating the coefficient of either the impedance or the admittance to the inductance or capacitance. And I mean, what is S equal to infinity? S is equal to infinity is nothing but the frequency at which the either the impedance or the admittance goes to 0, right? For example, if you had simply an LC, if you just had an LC network, right? At S equal to infinity, what is happening? We are able to equate, we are able to find this guy by equating this looking in impedance at S equal to infinity, simply because the impedance following, that is here, that is becoming 0 at a particular frequency, that being S equal to infinity. Now what is the difference? Pardon? Now all that is happening is that 0 is not happening at S equal to infinity, but at some finite frequency which we know to be equal to plus minus j omega z, which is 2 by plus minus j2 by root 3. Is that clear? So which is why I kind of motivated this by writing this. Earlier, when we had simply the LC all pole ladder, we would find Zn of S, and we know that to be SL1 plus something else. That something else starts with a shunt capacitor, and it goes to 0 at S tends to infinity. So by simply looking at the behavior of Zn as S tends to infinity, we'd simply directly be able to determine L1. Is that clear? Now we apply the same logic here, except that we now are interested in not at behavior at S equal to infinity, but at S equal to a finite zero transmission. Okay. So again, Zn of S, which is this impedance here, is SL1 plus Zn1, right? This is what I call Zn1. Everybody agrees? Okay. Now we know that Zn1 is a series LC branch. This must become a short circuit at what frequency? We are interested in making this a short circuit at the zero of transmission, namely omega Z1. Okay. So if I evaluate Zn of j omega Z at, Zn of S at j omega Z, then that must by definition be equal to j omega Z times L1 plus Zn1 evaluated at j omega Z. But we do know that Zn1 evaluated at j omega Z must be 0 because of the series LC branch. Is that clear? So in other words, L1 must simply be equal to Zn evaluated at j omega Z divided by j omega Z. Okay. All right. So there are two ways of figuring L1. Okay. What is that? If you're doing it on a computer, what would you do? You would evaluate this function at j omega Z and then divide by j omega Z, and you will get L1. Okay. But if you're doing it on paper, what would you do? You can say, I will now evaluate. One thing I could do is plug in S equal to j omega Z in this expression and go through the maths, right? But can you think of something, you know, what do you call, I wouldn't say easier, but something less messy? Okay, so equivalently, this can be written as or Zin of S minus SL1, right, becomes equal to 0 at S is equal to j omega z. Okay, so let's try and do this now. So what is Zin of S? For me it's quite easy because I just need to cut and paste. You understand? So this is what now? This is 2 minus 0.6746 L1 times S cube, correct, plus 0.6746 S minus 0.2271 L1 times S square plus 0.2271 minus 0.04 L1 into S plus 0.0400 divided by whatever d there is. Let me just call this d1. Okay, is this clear? Okay, now people, how many of you have calculators with you? Oh, very good. Okay, now please don't peek into your neighbor's thing, because it's likely that he also makes a mistake and we all make a mistake, and then we have to go through all this messy calculation all over again, right? So please do it independently, and then we do majority wins. So we need to evaluate this at S is equal to j omega z and find, what are we trying to find? Find L1 such that when this expression is evaluated at j omega z, this becomes 0. Is this clear? And if this becomes 0, we don't need to worry about the denominator, we just go ahead with the numerator. Okay. So I will just equate the real part of the numerator to 0. So 0.76746 minus 0.2271 L1 times minus omega z square, right, plus 0.04 becomes equal to 0, which means 0.04 divided by omega z square must be equal to 0.6746 minus 0.2271 L1, which means L1 is what? 2.8384. Again, it's very tempting to just knock off digits after the decimal point, right? But as I told you earlier, error will tend to propagate. So at all points in the calculation, it's just simply to carry, if you are working for an nth order filter, n decimal points after the n places after the decimal point. Okay. So can anybody else confirm that this is the answer? Yes? Okay. So we assume this is the right answer. All right. So, okay. Now I just like to bring your attention to what we did using the ladder when we had just an all pole network. What did we do? We first found L1, then what did we do? We subtracted SL1 from, we knew Zin, we found Zin1, which is Zin minus SL1, and that should give us the impedance at this node, right? But then what did we do? We said we know that this must go to infinity at this admittance, 1 by Zin1 tends to infinity at s equal to infinity. This is what we did earlier, right? And that is because s equal to infinity happened to be a pole of y1 or equivalently a 0 of z1. Now what is happening? What is the difference between that situation and the situation we have now? All this action is not happening at s equal to infinity, but it is happening at s equal to j omega z. So the procedure is the same. Thankfully, we can reuse much of our calculation. Okay. So the next step, therefore, is to observe that Zin1 of s, which is Zin of s minus SL1, goes to 0 at s is equal to plus minus j omega z. In other words, yn1 of s equal to infinity at s is equal to plus minus j omega z. Is this clear? So what is we now need to therefore find Zin of s minus SL1. Can we find it or not? We can, because we know Zin of s. We've just found L1. So how do we find Zin of s minus SL1? Please help me out here. We've already found L1. So plug into this equation and tell me what the polynomial is. All right. So after calculation, we found that the expression for Zin of s minus SL1 is this character here, which means that the admittance seen after the first inductor arm is yn1 of s, which is this character, simply the reciprocal of Zin1 of s. Now yn1 of s can be written, we know that yn1 of s has a pole at omega z1, and where do you think that pole is coming from? It is coming from the series arm L2 C2. So, and what is the admittance of the series arm? So this has a pole at plus minus j omega z, correct? And just like in the LC ladder case, all pole ladder case, the admittance pole was coming because of the capacitance in shunt. That was the frequency at which the capacitor was admittance was going to infinity, right? Now here also the reactance goes to infinity, but it goes to infinity at a finite frequency plus minus j omega z. So what is the admittance of, so the conclusion therefore is that yn1 of S has poles at plus minus j omega z, and that pole or those poles must be coming from the shunt arm, which is the series LC network, correct? So what is the impedance or the admittance of the series arm? Its admittance is SC2 by 1 plus S square L2 C2. Why does this make sense? It comes out of the math, all right, but can somebody quickly also tell me what the that's okay. At DC, how does this look? Okay, that's the zeroth order approximation, right? So can you tell me the first order approximation at DC, how does it look? At DC, the inductor impedance is very small compared to the capacitor impedance. The two of them are in series. So at low frequencies, the impedance must look like that of a capacitor, which means that the admittance must look like SC2. So in this expression, if you set S equal to 0, the denominator goes to 0 and the numerator goes as SC2, which makes sense, right? Similarly, at very high frequencies, how should this look like? It must look like an inductor because the capacitive impedance is negligible in compared to the inductive impedance, and the two of them are in series. So at very high frequencies, it must look like an inductor. It must look like an open circuit, but a better approximation is that it looks like an inductor of value L2. So as S tends to infinity, the admittance must tend to 1 by SL2. Do you see that happening? Yes. So this expression makes sense. Okay. All right. So yn1 of S therefore must be SC2 by 1 plus S square L2 C2 plus the rest of it, which is yn2 of S, because this network is, yn1 is a shunt combination of two admittances. The first admittance is that of the shunt arm, right, which is SC2 by 1 plus S square L2 C2. The other admittance is this character here, which is yn2. Does it make sense? All right. Now, and we already know yn1 of S. Okay. So now how do we find SC2? As S tends to infinity, what happens? Somebody, yn2 of S is definitely not, okay, is 0 at as S tends to infinity, yeah. So is, somebody remarked that as S tends to infinity, yn2 is 0, but so is this character. What did we do in the LC case?
So here we can get a relation to L2 and C2.
Okay, one apparent thing is that 1 by square root L2 C2 must be equal to omega z. Sure. So in other words, once we find C2, we can find L2. Okay. But the question is, how do we find L2 in the first place, or C2 in the first place? What all do we know? If yn1 of S has a pole at plus minus j omega z, okay, and that can be decomposed into the sum of two things. right? So around S is equal to plus minus j omega z, y in 1 will be tending to infinity, right? So if the left hand side tends to infinity, the right hand side being equal must also tend to infinity. But so which of these two terms will contribute to the infinity? The first term. You understand? Okay. All right. So now what do we? I mean, so how do you find SC2? Pardon? Not as S tends to infinity. Omega z. Is this clear? So all that they're saying is that around S is equal to plus minus j omega z, right? Y in 1 of S tends to infinity because plus minus j omega z are poles of y in 1 of S. But y in 1 of S, as we have physically seen in the network, is broken up into the admittance of the shunt arm as well as the admittance of this SL plus SL3 plus 1. Clearly SL3 plus 1 cannot go to infinity at plus minus j omega z. So it means that all the tending to infinity behavior of y in 1 of S is all coming from this character. Okay, so now how would you go and figure out SC2? Because it is 1 by SL plus.
No, in this case, like it is just a inductor, we can say, but suppose it has another branch after that, it is not a single branch.
Pardon?
If it had another parallel branch after that.
No, this is the way the network is constructed. It's not a blind statement. You understand? So the question was, okay, in this particular case, this doesn't tend to infinity, which is why you're able to use it, right? I mean, the argument is yes, we have constructed the network such that the 0 is given by L2C2. Okay. All right. So, okay, given that this is true, how would we go and figure out SC2, people? What happens? So what should I do now to find SC2? So multiply y in 1 of S times 1 minus 1 plus S square L2C2 by S evaluated at S is equal to either plus or minus j omega z. This must be equal to C2. Okay. Now, if this must yield a limit as S tends to at S equal to plus minus j omega z, it must therefore follow that what is this character at j omega z? 0. You are taking something, you are multiplying it by 0 and you are getting a constant number. Clearly what must be happening? In other words, the denominator of y in 1 of S must have a factor 1 plus S square by omega z square, just like what we saw here, right? So when we do the multiplication, we see that the z minus 1 go away, right? In a similar manner, the denominator of y in 1 of S must have a factor of 1 plus S square L2C2, which will cancel off this numerator and you get a constant. Is this clear? Okay, so now guys get to work and let's figure out what C2 is. This is y in 1. Okay, so you verified that this is 0.0400 plus 0.1136 times s. Okay, so this and this go away. All right, so C2 is therefore 0.6746 s square plus 0.2271 s plus 0.0400 divided by 0.0852 sorry 0.0400 plus 0.1136 s times s, this evaluated at plus minus j omega z. Okay. All right. Can now somebody evaluate this and tell me what C2 is? All right. So people have confirmed that C2 is this. So, and omega z, as we know, is 1 by square root L2 C2. Omega z is known, and that is 2 by root 3. L2 is not known, C2 is known, which means 4/3 is 1 by L2 times C2. So, what is L2? Right. 0.1327, 201. Okay. Looks like more than one have got the same answer. Okay. All right. So, in other words, what we have therefore seen is, so we now have figured out L1, we have figured out C2, we have figured out L2. Okay. And we know y in 1. Okay. Which therefore means that we know y in 1, we know L2 and C2, which means we can go and find y in 2. Okay. So, you can see it is indeed quite a job. So this is the expression for y in 2. So please go ahead and evaluate what this this comes out to be. We already know that this can be factored as one plus s square into 3 by 4 times point 1136 s plus point okay, which is therefore means that y in 2 of s is 1 plus s square 3 by 4 0.1136 s plus 0.0400 times the numerator. Can somebody evaluate the numerator, please? So as you can see, this and this slightly off due to numerical round off. So the true thing must be 0.03 s square plus 0.04 divided by 1 plus s square into 3 by 4 times 0.1136 plus 0.04, which therefore means that this can be, the numerator can be rewritten as 0.04 times 1 plus s square into 3 by 4, and this cancels with this, and we are left with 0.04 divided by 0.1136 s plus 0.04, okay, which is 1 by, what is that? 2.838 s plus 1. So this is the admittance. It can be, and apparently it is the sum of, is the reciprocal of two things in series. So these must be impedances, which must therefore be modeled as, this must be L3, and this of course is the terminating resistance. Okay. So what is the final network? The final filter network therefore is one ohm, 2.838. Okay. What about the, what is L1? 2.838. Okay. What happens to C whatever, C or C2? 5.67. And what about inductance? Okay. So finally we have finished. So far we have seen how to synthesize Butterworth, Chebyshev, ordered Chebyshev and inverse Chebyshev filters. Okay. We will continue with some observations on the properties of doubly terminated ladders, and move on to the next topic in the next class, that is Wednesday 11 to 12. Okay.